So thank you all for coming on this day of water conservation. Today we're very happy to have Luca Orusa, who did his PhD in Torino before moving to a superposition in Princeton and Columbia, although apparently it's sequential, not parallel. So he's going to tell us about energy gamma ray stuff. So please go ahead.
Thank you, Aaron. Thank you for having me here. Thank you for coming. I really appreciate considering Water Plus Readings Week. Today I will talk about the positron excess in cosmic rays and how we can get some complementary information from gamma ray observations about that. And this presentation is based on this series of papers that I mainly did during my PhD at the University of Torino, plus a few new interesting things that I'm working on with Lorenzo Sironi at Columbia. I will jump around between very different physics topics. So if something is not clear, please just feel free to interrupt me. Okay, let's start from what is probably the most famous plot in cosmic ray physics, which is the cosmic ray flux, the total cosmic ray flux that we measure, with several different experiments that are here listed and with a very different and various chemical composition. And the cosmic ray flux span a large number of degrees, both in energy, we can go up to 10 to the 20 electron volts, and also in the total flux. And on average, we can kind of model this cosmic ray spectrum roughly with a power law. But even with your high, you can see there are a few features there and there that can tell us about quite some interesting physics. In particular, the main idea is that up to a few PV, the origin of cosmic rays is galactic, so they must be produced probably in supernova remnants. There could be other sources, in particular in the high energy region, and we usually detect most of them actually with space-based experiments, so they are satellites that directly take data. But at the border of PV and then for the higher energy part, we're talking about the ground-based experiment that just detect the primary cosmic ray that interact with the atmosphere, produce a shower, we detect the shower, we can reconstruct the energy of the primary. If you're interested in how we can accelerate particles, this is a different part of my work, which I'm very happy to chat if you're interested, and we can start using plasma simulations, but I will not cover this topic today. As I mentioned, most of the rest of the cosmic ray flux, we expect it to be actually of extragalactic origin. And if we go in that regime, stuff gets even more complicated. We don't really know what are the sources of ultra-high energy cosmic rays, how they get accelerated, stuff get messier. But we will focus today only on this galactic part. And in particular, we will focus on a subsection of the galactic cosmic rays, and in particular on the lepton component that we measure. So this is the total electron plus positron flux that is measured by different experiments, IMSO2, Dampe, Calet, etc. And in particular, most of them are space-based experiments, but more recently also the S collaboration was able to actually provide a flux. So this S is a ground-based experiment, provide a flux for the cosmic ray electrons, and that seems to show a sort of sharp cutoff. But while most of the electrons are produced probably in supernova remnant, etc., an interesting, a small section of the electron plus positrons flux is made, of course, of positrons, which are subdominant for fairly obvious reasons, which is our universe is made of matter, and positrons is antiparticles. And so, of course, we don't have too many antimatter sources in the galaxy. And the positron flux, which we measure with the magnificent experimental data provided by IMS, show quite a few interesting features. In particular, this rise in the flux that will be the main focus of this talk. Now, how we can model and how we can study and basically understand where cosmic ray positrons are produced and what are the sources that are responsible for the data that we see. Well, to study just the cosmic ray positrons without considering anything else, we need to combine physics at dramatically different scales. We have to go from particle physics scales in the cross sections that I will show you later. We need to model the plasma physics that is responsible for the particle acceleration and how positrons can get accelerated up to those energies, which is in the plasma physics realm. We have some interesting phenomena that we are detecting on parsec scale called gamma ray halos that I will cover later. And then we have to talk about also propagation in the galaxy of particles on sizes that are of kiloparsec scale. So even just to study positrons, we need to take into account of all these different physics regimes. Now, let's start from this last point, and I will try to give you an overview of how we usually perform study on cosmic rays in order to explain the data that we measure. Now, the standard model of cosmic rays can be basically summarized with this picture. So cosmic rays can be produced somewhere by a source that you can choose and that you can pick up, but they are charged particles. And in our galaxy, we have a magnetic field, so they will not travel straight, but they will undergo a random motion due to the fact that the galactic magnetic field is not just a regular magnetic field, but it's made of discontinuities and waves, etc. And so particles, once they are produced somewhere, will basically scatter and undergo a random motion in our galaxy. And in particular, the idea is that they perform what we call the diffusion process, which is this random motion, into a region that we call the galactic halo. And the basic idea is in the standard models, we model the galactic halo as a cylinder, nothing more complicated than that. And particles usually can diffuse isotropically in the cylinder. And once they reach one of the boundaries, they're just free to escape and go away. Of course, we don't have only diffusion processes going on. We can have some additional term called, for example, reacceleration, in which particles can actually get a little bit of energy from scattering with these magnetic field discontinuities that are in the galactic magnetic field. We can have convection, that is basically just a wind coming from the disk and pushing cosmic rays away from the galaxy. And in general, anytime a cosmic ray is traveling into the interstellar medium, into the galactic disk, which is a disk that is much smaller than the overall halo, they can interact with the material that is there, the interstellar medium, which is mainly made by hydrogen and helium. And so there is a certain amount of probability that an energetic cosmic ray will interact with a particle of the ISM and produce what we call the secondary cosmic rays. So we can already make a distinction between primary cosmic rays, which are produced and accelerated in astrophysical sources, supernova, pulsar, whatever you want, and secondary cosmic rays, which are a byproduct of the trip that cosmic rays do before reaching the Earth. Now, if we translate this nice picture into an equation, this is what we get. This is the transport equation that codes like Galprop, Dragon, Usin, etc., solve. And all the effects that I listed you before are basically a term of this equation that we solve in this cylindric geometry that I showed you earlier. In general, the most interesting, the most important thing that we want to model is the diffusion process, which is this random scattering that is usually modeled as a power law in rigidity. There are many physical reasons why this is the case, but for the moment, just trust me. We have the source term, which again models how many cosmic rays are pumped into the galaxy at each time, and we know that particles get accelerated like in supernova with again as a power law in energy. So again, this is a term that enter our equation, and we can play with the slope of this power law when we model, and then we have all these other terms that enter and that we need to take into account. Okay, let's start focus on positrons. So for sure, for positrons, as I mentioned, there must be a secondary component of positrons, which is the one produced by cosmic rays traveling to the galaxy, interact with the interstellar medium. And this is an unavoidable component that we need to know and that we need to model properly, in particular if we're interested in seeing if the secondary positrons are enough to explain the data that we see or not. Spoiler, they're not. And then we can have some primary component that we need to identify somewhere, and we will get to that later. So let's start from the secondary particles, because we need to have a precise prediction on the secondary component of positrons. And to do that, we need to model how many of them are produced in an interaction. So this is the source term for a secondary contribution of positrons that enter in our propagation equation that I showed you earlier. And you can find several terms. There is the density of the interstellar medium, which is your target. You have a flux of the cosmic rays that impact on this target. And then you have this quantity, which is the production cross-section of positrons from an interaction of a cosmic ray particle with a particle of the ISM. Now, the main channel of production of positrons are just classic proton-proton collision. So a cosmic ray proton that impact on a proton of the ISM. And from this hadronic interaction, we will have a list of intermediate particles that can decay and produce a positron in the final state. And so in order to have a model of this quantity, we need to calculate the contribution coming from all these type of reactions. Well, what we can do to do that? Well, this type of interaction is exactly what we can do into accelerator experiments. And so we can take the data from experiments like LHC at CERN or anywhere in the world, like any cosmic ray, any proton beam can detect impacting with something, can produce this type of measurements, and we can fit those data that we have available and have a model for these production cross sections. In general, before the work that we did, the uncertainties on the cross section were actually very large, were almost a factor of 2, and this can give you a large uncertainty of how many secondary positrons you expect in your data. So we did a fit. We collected all the possible data, and this is the result that you get. This is the production cross section as a function of the positron energy for 2 incident proton energy, just for example. And the main channel of production is the pion, but you need to model also all these counts, et cetera, and take them into account. The interesting thing is that if we look at the uncertainty of our model is now dramatically small because the data that we have from accelerator experiment are dramatically precise. And so we can tune the uncertainty on our cross-section directly on the uncertainty that we have from particle accelerators. And okay, this is great. Now we have a good model for the production of positrons. If you're interested in the world of cross-section for astroparticle physics, this is a topic that is getting more and more attention, and people are paying more attention also at CERN. And basically, all of this effort resulted in a white paper that has been accepted by Physics Report. It's a 100-page paper that is also an overview of all the things that we need from the particle physics point of view, from the cross-section physics point of view, to perform study in astroparticle physics. So if you're interested in that, have a look. And also, I know that here you have a proton beam. And I know that it's operating at GeV energies, which are exactly the one that we need. So if you work on that, I would be very, very excited and happy to talk if we can do something or propose some measurements also here. And in my group specifically, we focused, we did this with these 4 papers on antiproton, positrons, gamma rays, and more recently neutrinos. So if you work in IceCube and you are modeling the production of neutrinos in the galaxy, use these cross sections, are the best. And personally, I just work on the last 3 papers because in the first one I wasn't born scientifically yet. But yeah, even if you don't want to read because they're extremely boring, you can just take the conclusion, take the tables. There is a GitHub page with all the tables and a script to read them, so you don't have any excuse to actually use these results. Okay, so now we have the cross section. Let's have a look again at our source term for secondary positrons. So we have the cross sections, fine, we have a good model for that. We still miss the cosmic ray flux that interact with the ISM and produce positrons in the final state. So in order to fix our primary cosmic rays that interact with the ISM, what we can do is to use a code like galprop and basically model and try to perform a fit to all the different data that we have from the IMS collaboration on primary cosmic rays, secondary cosmic ray, etc., testing different propagation models that can all be free parameters that we can tune and fit to the data and produce a prediction. So from the fit to all the data, we can basically fix our propagation model. Of course, there are a lot of potential degeneracy between the different parameters and the different physical effects that are turning on and off. So the idea of our work was to basically try to explore all the possible realistic propagation model that we can have and we can model with GalProp, try to fit all of them to the data, and then have a look at what type of secondary positrons we will get in order to have a sort of uncertainty on our secondary positron production based on how much uncertain are our propagation models. And you can see that even if we tested several models, if you want the details of the models, I'm happy to give them to you. But in general, no matter is the propagation model that you use, you will always find that the data will be much higher than the secondary positrons, which are this solid line prediction that you get, with a specific focus on this large excess that is here. Yes.
And the planner analysis here. You use several propagation models that you fit to the AMS cosmic ray spectra, and they were talking about like the protons that and then from that you try to determine what the truth level cosmic ray spectrum is. These are your secondaries, and then those are the different predictions.
Exactly.
So is there a lot of variance in what you get as your predicted cosmic ray spectrum based on your propagation and or diffusion models, or is it basically very flat? Basically what I'm asking is there like a spread in what you predict? Is the spread of the proton, for instance?
Okay, sorry. I mean, of course.
I mean, at the end, you always need to fit your data. So like you can have some model that works a little bit better than the other, but the sort of prediction here is always the same because you have to follow your data. But the parameters that you use in your propagation model to explain the data can change a little bit. And so since we are not performing a fit to the positrons, for the positron, we're just looking at what is the final result. Basically, from all the different propagation model, we can get a different prediction for each propagation model in the positrons. And this is the variance that you get.
I know your question, but do you have to also try different like source models, like how far away you think the galactic cosmic rays are coming from?
Yeah, can play a little bit with the radial distribution of sources, but again, that's a free parameter that you put. I mean, there is always, like, you can do as much as you want and change as much as you want. And you can actually add even more uncertainty here based on the size that you put in your diffusive halo. That actually has quite an impact on what's the positron prediction. But the general idea is that you can also have let's say, get a line that goes up to here, but it will always go down. And so you are always left with an excess that you need to explain somehow. Yeah. So, okay, how to explain this excess? Well, the standard candidate to explain this excess are pulsars, which are natural factories of electrons and positrons. And the basic idea is that these pulsars have such strong magnetic field that can extract electrons from the surface. This electron will propagate in strong magnetic field, will produce gamma rays, then again will produce positrons, and you get a sort of large cascade of pairs that basically creates this what is called the pulsar wind. And the pulsar can evolve in a very complex environment. At the beginning, they live inside the supernova remnant, that is their parent. The pulsar is basically a relic of the remnant itself. But they usually are born with a sort of kick velocity. So at the initial stage, they will live inside the remnant, but eventually they will be able to exit the remnant and just propagate into the standard interstellar medium and form what they're called bow shock pulsar wind nebula. In general, when they're still inside the remnant, the physics going on there is quite complex, but we see from multivariate observations that particles can get accelerated in this pulsar wind nebula system up to very high energies, even PeV energies potentially. And the idea is that based on some type of emission and escape model, these electrons and positrons, once they are accelerated here, they can reach the interstellar medium, propagate, reach us, and maybe explain the positron excess. So in a paper that we did a few years ago, what we did was we detect around 3,000 pulsars that are there in our catalogs. And but we're not sure if this catalog is complete. Actually, probably it's not. Because maybe the pulsar is not pointing towards us, or it's too faint to be detected, et cetera, et cetera. So what we did was actually to, okay, instead of taking the catalog that we have, let's build a fake galaxy of our pulsar population based on models that were provided in the past, that were tuned on the pulsar that we actually observe. And let's create several fake galaxies. Let's try to compute the positrons from each of these, the positron flux coming from the pulsar of each galaxy, testing different models of propagation, of injection, et cetera, and let's have a look at what is the characteristic of the galaxies that can actually explain the positron excess, and sort of back engineering and understand what properties the pulsar should have or the galaxy should have in order to explain the excess that we have. Now, this is just a general list of equations for which you can model your pulsar emission. The idea is that you basically convert a certain amount of the rotational energy of the pulsar into energetic particles, and it's a certain efficiency that it goes with eta. And in general, the energy spectrum that is tuned to multiwavelength observation is that pulsar accelerated particle with a basically broken power law in energy. And their emission also decays with time with a certain value tau zero, which depends directly on their initial period that they have. So great, we take each of these galaxies, we calculate the positrons coming from each of these galaxies, we perform a fit. Some of the galaxies work, some other don't. And these are just two examples of two galaxies that perform a good fit to the data. So you can see that the total positron flux coming from pulsar is this blue line that can quite well reproduce the excess and does a quite decent job. And in general, already from here, visually you can see that most of the work, most of the positron production seems to be dominated either by one single source or by just a few. And you have, of course, a sea of contribution. Each line here is a single pulsar, basically, in your galaxy. And but overall, you just have one or a few dominating sources doing most of the job. So we try to quantify in our different model that we tested how many sources we actually need, based on a threshold method, which is directly tuned on the uncertainty error of the IMS data that we're trying to fit. But in general, we can count a very, very few sources, 3, 4, that do most of the job. And in particular, these sources are characterized by ages that are between 400 and 2,000 kiloyears. So they are so-called middle-aged pulsars. And they are fairly powerful, not dramatically, but fairly powerful. And they have a distance that is less than 3 kiloparsec. Okay, so in the end, what seems to be is that actually most of the positrons seems to be produced fairly locally. And so we don't really need to care about positrons that are produced on the other side of the galaxy. This is also due to the fact that electrons and positrons cool down very quickly when they travel due to their energy losses. For example, protons don't really care about energy losses. They don't lose a lot of energy while they travel. Electrons and positrons do. You have inverse Compton, you have synchrotron radiation. And so positrons should probably be local. If they are local, then we can make the next step, which is actually go back to our catalog, because probably the catalog is already doing a decent job in covering all the pulsars that are in the nearby that can potentially produce the positron excess. Yes, of course, please.
So you simulate different galactic environments, essentially by just taking the existing pulsar population we've observed around us and then like plucking out a representative sample and then just scrambling around a bunch of different combinations. And you saw, okay. And then from that you saw, okay, so based on what we think we know about positron. All right, thanks, yeah. No, I don't have a question. Okay. I just want to make sure I understand. Yeah. Promise of that.
Yeah,
sure.
So you had all those different curves.
Yes.
What sets the upper limit on the energy?
Here?
On the previous slide. Sorry. You have these cutoffs at energies at different energies for different pulsars.
Yeah. Okay.
What's determining those energies?
Great question. So that basically depends on the age of the pulsar itself. Mainly, basically the idea is that if the pulsar was emitting, let's say,
there is a combination of two parameters. It's both the age of the pulsar and also this tau zero, which basically tells you how quickly the pulsar is emitting and how quickly also its power is decaying.
So you have a large tau zero, basically the pulsar is emitting for a longer time efficiently. If the tau zero is very small, basically the pulsar is losing, like it's converting very quickly all its rotational energy, and so is almost a burst-like source. So basically, if we assume that a pulsar has emitted all of its particles way early in his life, those particles were emitted immediately, and then they cool down. And so that tells you, and the cooling time depends also on the age, of course, because they were emitted only at that point. So they cool down and you get this. If on the other hand, you have a tau zero, for example, let's assume the pulsar has the same age of the one that I just explained, but tau zero is much longer. Particles like energetic particles have been emitted also at much later time. And so they have had a shorter time to cool down. And so you can get particles also at higher energies.
Reason on this plot that you have most of your signal 1 to 3 kiloparsecs is any closer than that, and the idea is you don't get a population of pulsars that are young enough to give you an energetic pulsar wind nebula. And any further than that, then there's propagation effects that kill off your positron energy.
Exactly. I mean, these are two. You can get also the pulsar, and not in these two specific cases, but you can get pulsars also that are much closer to us, not necessarily between 1 and 3 kiloparsec. But the upper limit on 3 kiloparsec is basically because of propagation and cooling effects. So yes, it's a sort of like if you were born at 4 kiloparsec, before reaching us, you have lost most of. Like if you were born. A particle was born at 2 TeV at 4 kiloparsec, it arrives to us that it has an energy that is like.
But in these two examples, at least the very light lines, which correspond to less than a half kiloparsec and half to 1 kiloparsec, I just don't see them contributing very much.
No, in these two specific cases, no. But we have because of course we did many galaxies, so these are just two examples. We can have a case in which you just have one of these. Over there, and it's very powerful.
So if you get a young one nearby,
it can still do the job. Let's say if they are too young, that's a problem because they will probably emit this region. But if they are in the middle age region, so of the order of a few hundred kilo years, you're fine.
Interesting one that we actually want to model. So we moved then to the, okay, let's actually have a look at the one that we have in the catalog, because now we are assuming that probably the catalog that we have is fairly complete. We take the characteristics of position, age, and spin down of the rotational energy, basically, from the catalog, but we need to simulate all the other parameters that we cannot measure, unfortunately. And we simulate them basically with the same models that we were adopting in the previous analysis. And again, we are testing several models, both, for example, tau zero, which is the parameter I was mentioning before. We do a case in which it's fixed, as many people did in the past. We actually can drive a distribution of tau zero that we can assign to each pulsar. We can assume that only a certain fraction of positrons is considered. Basically, there are a few uncertainties about if the positrons that were emitted while the pulsar was still inside the remnant should contribute or not. So we can separate the two contributions and see how much our results change. And then there is this two-zone diffusion model that would be the main focus of the last part of my talk, in which we are basically assuming that close to these sources, the diffusion process that I mentioned you at the beginning is different with respect to the rest of the galaxy, since we have some indication that this might be the case. So again, we do the same job, but this time all this single contribution that you get, these are all from real sources that we model in all the different ways. And again, for some of the model, we have again a pulsar that is almost doing all the job, like here or there. While in some others, we have a few of them that are actually let's say contributing at similar levels, and at the end you always have also a little bit of C of contribution that is doing a little bit of the overall job. But Okay, so actually, the point is that we have 2,000 and more sources, but how many of them do we actually care about? So to make things a little bit more quantitatively, we took for each simulation, we took the simulation that actually work and can feed the data. We took the 10 brightest sources, and we calculate, if I just consider the 10 brightest sources, how much positron flux is produced over the whole positron flux coming from the whole pulsar population. And the answer is that it depends a little bit on the model that you adopt. For example, if you assume this decay time fixed for everybody, you can have some more comparable contribution. But with the most 10 brightest sources, you have you can produce more of 50% or higher of the total positron contribution. While for other models, you can basically explain with the 10 brightest sources within 80 or 100% of the overall positron flux coming from the population. And so in the positron excess, actually, on average, you usually care, at least at energies higher than 100 GeV, you usually care only about your first 10 brightest sources. And also, one thing that we wanted to check is, are these 10 brightest sources always the same, no matter of what type of model we adopt, no matter of the simulation that we do, etc.? Can we build a sort of statistical hierarchy, or which are the most important sources? And the answer is yes. And basically the 10 brightest sources are kind of usually the same for all the different models that we tested. And then we can build a final list, which is the list of the 10 most important sources that should be responsible for the positron excess after all the statistics that we did. And again, they are all fairly close, not too distant, middle-aged pulsars, and fairly powerful. Now, this is basically target list that we are trying to give and promote, because these are the sources to which we should focus for multi-wavelength observations and try to get some sort of comparable characteristics of them on which we can tune our model and actually prove if these are the most important one or not. Like, I would be happy to people like find that this one maybe are not important at all, but if you just look at the positron excess, this is the list that we should care about, and they should be the target for multi-wavelength observations. In particular, one thing that we should look for in all of these sources are what we call the TV halos. TV halos are a new, that you can find over there, are a new detection that has been provided by the Hawke experiment, but also LASO more recently, in which, and basically I'm talking about an extended gamma ray emission coming from a few pulsars of our galaxy, like Geminga, Monogen, and these other sources. And we're talking about an emission at TV energies, so very energetic gamma rays, that spans a few parsec. So it's a very, very, very extended emission. Now, the interesting thing of TV halos is that they can give us some sort of complementary information with respect to the positron excess. In the positron excess, we are looking at particles that has been emitted somewhere out there. They traveled a lot. They cooled down. They were affected by energy losses, and we just see the results. Here, on the other hand, we can get some interesting information about what are the particles that are producing these gamma rays. In fact, the main idea is that this gamma ray emission can be explained by the electrons and positrons produced and emitted by the pulsar, that they perform inverse Compton scattering with the photons of the interstellar radiation field and created this gamma ray halo. So looking at this gamma ray halo, we can see what are the characteristics of the particles very, very close to their sources, and how do they propagate, and what, in general, what we need in order to explain this type of emission. In general, an interesting result in order to explain this type of emission is that the diffusion process that before we always modeled as isotropic in the whole galaxy, it seems actually to be much, much suppressed close to these pulsars. What does it mean? Basically, it means that particles, instead of, basically they are scattering more close to their sources. And so this random path, basically they tend to be more trapped close to these pulsars, and they struggle to actually escape away. How can you obtain such effect. It means basically that the properties of the magnetic field locally to the pulsar environment is very, very different with respect to what are the properties of the magnetic field in the rest of the galaxy. And how do we explain that? Well, there are a few ideas, and it's a still very, very open problem. So the inferred diffusion coefficient is 100 times smaller than the one that we have in the rest of the galaxy, so it's quite a lot. And a way to explain this is that all the TVLs that we see, that at the moment are 3/4, so there are not many, all the TVLs that we see are associated to pulsar, which are still inside their supernova remnant. Now, if this is the case, what happens is that the supernova remnant explodes, accelerate particles, you have a shock that expands into the interstellar medium. And so since the shock passed through the interstellar medium, the turbulence properties of the shocked region is different with respect to the one that is outside of it. And so you can actually suppress the diffusion coefficient considering the turbulence produced by the shock itself that just passed through that. And there was this nice, interesting paper that came out this year in which they were sort of trying to find a statistically if all the TVLs that we see are actually associated with a pulsar which is still inside the supernova remnant. The answer is that for 3 of them, it may work. For a 4th one, you really, really need to stretch the calculations that you do in particular, the pulsar is Geminga, in order to assume that the pulsar is still inside the remnant. The main problem is that for these pulsars, they are too close to us, and usually we don't detect the supernova remnant itself. So it's difficult to understand what is the environment in which they are. A different approach, on the other hand, is that the magnetic field properties close to the pulsar and pulsar nebula are changed by the electrons and positrons produced by the pulsar itself. Electrons and positrons are charged particles. They're very energetic particles, and they can basically trigger what we call plasma instabilities and heavily modify the environment in which they are propagating. There are several possible plasma instabilities that has been invoked. The one that probably can be more optimistic about that is the so-called Bell instability, which is also often invoked in particle acceleration of shocks. And the assumption is that this Bell instability can grow very fast if you have basically a beam of particles propagating into a background plasma. The background plasma in this case is the interstellar medium. But the problem of the Bell instability is that in order to trigger it, you need a net current. And in the standard picture, the number of electrons produced by a pulsar is equal to the number of positrons produced by a pulsar. So you have charged particles, but the total amount it should be the same. And so you have a 0 net current. And so how can you trigger the Bell instability for this case? We will get to that later. Another object that has been recently detected that seems to have some sort of similarity with the TVLs are these X-ray filaments that have been detected around a few pulsars, which in this case are interpreted as, again, the electrons and positrons produced by the pulsar that travel along a local magnetic field line, and they perform synchrotron radiation and produce the X-rays that we detect. Again, the size of these objects, I'm talking about, again, a few parsecs, even 10 parsecs for some of them. And in order to explain how bright they are, in this paper by Barmar et al. And collaborators, they were interpreted as, again, we have particles produced by the pulsar. They are streaming into the local magnetic field. And so you have basically an energetic beam of particles propagating into a background plasma. And again, invoking this Bell instability, they're amplifying the field. So they're modifying the properties of the interstellar medium, amplifying the field and increase the diffusion process in these filaments and actually produce this bright emission. And again, also in their paper, they were assuming that there is a sort of asymmetry between the number of positrons and electrons that escape from a pulsar in order to have a net current. Well, personally, I'm not sure if this is the case. So yes, if this is the case, so a thing that we can do to study this type of problem is to actually perform kinetic plasma simulations. So particle in cell simulation or kinetic plasma simulation are a technique that is used and is quite computational expensive usually, in which basically you can sort of create a model, let's say, an idealistic model of your problem. And you basically take your space, your simulation, you divide the space into a grid, you put particles on this grid with some initial electric and magnetic field, and you move particles on this grid according to the Lorentz force. Since particles move on this grid, they can trigger themselves some modification in the electromagnetic fields. So you move particles, you gather the current produced by the motion of these particles, you modify the electric field, you move the particles again, and you keep going and going. So I wanted to tackle this problem basically, and my idea was that, okay, I want to see if a population of electrons and positrons produced by the pulsar and propagating into a background plasma, which is my interstellar medium, can change the magnetic field that I have at the beginning. I want to check if they can actually trigger some type of instability that can more heavily modify the properties of the magnetic field before this beam was going through that. So this is basically the model that we adopted at the beginning. At the beginning, we did 2D simulations, and in particular, so the idea is that I have my pulsar wind nebula producing electrons and positrons. I have an external galactic magnetic field, and particles are emitted from the nebula, and they just travel along the magnetic field. Now, I take a transverse cross-section of this sort of local flux tube that I have. And so if I translate this in my ideal simulation, I have this square with the magnetic field out of my plane and a beam of energetic particles of electrons and positrons that are traveling in the same direction of my magnetic field. And so the idea is that I just inject my particles at the beginning, and then I just let the system evolve with periodic boundary conditions all over. So, okay, let's see what happens. If I put enough energy in my beam, we can see that some magnetic field actually starts growing. So imagine that initially I have my magnetic field that is in this direction. I have the beam that are also flying towards you. This is the perpendicular magnetic field that is produced. So this is a field that wasn't there before, but is produced by the particles that are traveling. And here are the position of my electron and positrons of my beam. And so I want to track where they are and how they're placed with respect to these small pockets that you will see. So we initially see a little bit of small pockets of magnetic field amplification. This is called Weibull instability. It is a very well-known instability, which can come from an electron-positron pair propagating to a plasma. But let's see how it evolves, which is actually the most interesting part. So you see that they start merging, and the cavities get bigger and bigger, and some of them get much bigger. And if we wait long enough, let's stop here. Yes. If we wait long enough, we have only one cavity left, and that cavity is populated only by the electrons. And all the positrons are flying outside.
So the initial condition gives you pockets of electrons and positrons, the instability.
Yeah, it's like at the beginning, it's like imagine that everything is completely black. It's just that the output was a few times later. So at the beginning, you just have the order and magnetic field that is out of the plane, and then out of nowhere you have the Weibull instability that kicks in, and then.
And this is in the presence of the magnetic field. You get a little bit of separation.
Exactly, because the Lorentz force goes in a different direction. You get a little bit of anisotropy.
Yes.
This is you end up with one cavity populated only by electrons, and the fact that you get this the fact that only the electrons survive in the cavities is actually due to the fact that you start with a beam of electrons and positrons, but your background is not perfectly symmetric. Your background is made of electrons and protons. So the electrons of your background can easily counteract your positron of the beam because they are very light particles and they can actually kill all the cavities that you have. On the other hand, the protons of your background are very heavy and they will not compensate the formation of these cavities, of the electron cavities as quick as the electron of the background do for the positrons. And so due to this sort of asymmetric condition that you have from the beginning, you end up with only electrons living in the cavities and positrons flying outside. But so if I look at here in this region, I basically have a net current. because all the electrons are living in the cavity, all the positrons are flying outside. And why this should not produce the Bell instability that I was saying at the beginning. So you start with a perfectly symmetric beam, and then you created an asymmetric situation. The problem is that if you want to model the Bell instability, we need to resolve the dimension that we are not resolving now. And so we need to move to 3D simulations, which actually we did. And this is the result. So in this case, I have particles that are propagating along the z direction. The initial magnetic field is along z, together with electrons and positrons. And now we will see exactly the same thing. You will see exactly the same thing that I showed you before in 2D, but in 3D. So you have a little bit of mess at the beginning, which is the Weibel instability. And then you start seeing these cavities that look like donuts. And if you wait long enough, you get all this mess going on. Now, from this picture, it's not so easy to tell, but if you trust me, and because I looked at the waves, etc., this magnetic field that start populating all my box is actually produced by the Bell instability that I mentioned before, because I created a local asymmetry and a local current. And so from nowhere, from a system that wasn't supposed to grow the Bell instability, now I have it. But this is great, because the Bell instability is exactly the one that we need in order to explain, for sure, most likely, the X-ray filaments. And so this is can show you sort of the power of particle in cell simulation to actually get some interesting physical insight on some object that we see. And so for the X-ray filaments, this can provide a very, very good explanation of what we see. For TV halos, the situation can be a little bit more trickier. We definitely need much, much larger simulations, maybe also different computational techniques. But personally, I think that this type of mechanism can potentially work also in that case, but in my opinion, still an open problem. In general, the truth about TV halos will be, we'll discover when we will have many, many TV halos that are detected. And so at that point, we can make a study on if all of them are in a supernova remnant or all of them are outside, et cetera, et cetera. So for X-ray filaments, I think we are providing a fairly good explanation. For TV halos, we will see. Okay, so I don't know how much time do I have. I guess we're almost at the end. So these are sort of general and final picture. So these are all the elements that we need in order to perform a sort of multi-messenger if you want analysis of the cosmic ray positron flux and TV halos. Cross-section are okay. We have a good model for that. Propagation models, they are okay. They are phenomenology, and so we have uncertainties on that. And I will tell you a little bit more about that in a second. On how particles get accelerated in pulsars, that's a major uncertainty. I didn't cover this topic today, but we still have large uncertainties of how these electrons and positrons get accelerated into the pulsar wind nebula. Can be shocks like the termination shock, could be magnetic reconnection, open problem. On the TV halo and X-ray filaments, we're getting some very, very interesting results from particle in cell simulation. And I think in the next few years, it's quite a hot topic to keep working on due to also the more and more data that are coming. So these are the take-home messages, which is basically exactly what I told you. All the propagation models on the study of the positron success that I told you about today, everything is based on a very phenomenological approach. You have a model with many free parameters. You tune those parameters to the data, and again, you get your conclusions. I think that is also time, in my opinion, to go beyond that picture, try to actually put some more real physical insights inside our models, considering cosmic ray feedback, don't consider just anisotropic diffusion in the rest of the galaxy, and go and basically start working on an improved version of GalProp or something more, even more realistic. And to do that, we are organizing a workshop in Princeton at the end of February. This is the poster with all the invited speakers. The registration is still open, even if you want to send a contributed talk. If you're interested in that, this is the QR code. And if you've never been to Princeton, it's a lovely town, and spending a few days there is very, very nice. So with this, I thank you for your attention, and I will get any questions.
Thank you for the talk. Are there questions? If you're online and have questions, you can raise your hand.
Nicholas, so I had a list of questions, but you've answered all of them, so I have just one technical question. So you use caliper for all of this, right?
For the fit to the total cosmic rays, etc., yes.
Yeah.
For the contribution from the single pulsars, actually we were using an independent semi-analytical model, because with Galprop, now that they have the setup of having a single source, but if you try to use that with 2,000 sources, it's just impossible. So in that case, for that type of analysis, we are using an approximation based on a green function formalism.
Okay.
But considering that electrons and positrons are fairly local at the end of the day, it's a fairly safe approximation that matches quite well with the Galprop setup.
Okay, thank you. Yeah, for my research, I'm getting used to Dragon.
Okay, great.
Which is just,
I'm a big fan of Dragon.
yeah. And like you said, you have to make some modifications to the codes to get it what you want. So I was just wondering. Thank you.
Yeah. Dragon, yeah, it was written by people that I know. So
Okay, thank you.
Yeah, so this is like a basic question, but I'm not really in your field, so I get to ask this. What's the scientific output of studying all these like TV halos and pulsar wind nebulas, like, and the cosmic ray, like the positron excess and the cosmic rays? Like, is this like a standard model thing, or like?
Let's say it's interesting in order to understand let's say from the study of cosmic rays in general, we can understand a lot about basically how galactic sources work.
Okay.
So how supernova, how pulsar work, and how particles propagate into the galaxy. And all of this can have a lot of influence to many other studies still in astrophysical world, like studying how many gamma rays that you get from the center of the galaxy. Like everything is very like cross-connected, but the general idea is just that we want to know what's the acceleration process, why we get such energetic particles, how do they travel, and what's their life from the beginning to the end. And since we see all this data, and they're very deeply connected with several topics that they talk to each other. So I don't know enough.
Sure, yeah.
Could you say more about the magnetic field simulation?
Yes.
What the size of the box and what are you?
Yes. So, of course, I passed a little bit on this part, but it's just the videos it's virtual. Okay, if let's say, basically the parameters of my simulations are 3, which is the energy density of the beam that I put, which are my electrons and positron beam from my pulsar light, and I have the thermal and background energy of my background plasma. So basically the interstellar medium. So if I try to put a value, now the energy density of my beam is basically the gamma factor of my particles times their density. But if I try to put an actual density that is realistic to the one that I have in a pulsar with nebula, I will never be able to simulate anything, because the densities of the pulsars right in the flux tube are too low and are way low the noise level that we can probe with particle instant simulation. So what we can do is to actually take a realistic ratio between this quantity and this quantity, rather than put the exact values that we can have into that we can have in a pulsar with nebula. And the basic idea is that we want to find a hierarchy to when we are able to see something that grows based on the combination of parameters that we do. Now, usually to trigger something in this specific setup, to trigger this cavitation instability, we need this quantity to be 10 times higher than the other two. But if you make a calculation about how many particles you expect, about density of particles at TV energies from a pulsar in a pulsar flux tube, you can, it's not unrealistic to satisfy this condition. If the pulsar is too, it's not powerful enough, it may fail. But for let's say, classic middle-aged, fairly powerful pulsar, it can work. But there is a lot of extrapolation going on. Then about the size of the box, of course, we're talking about a very small size, but in this case, we're talking about was 48 electron skin depth, which is nothing. So what we are seeing is truly like the beginning of this process. But that's the best that we can do in unfortunately with this type of technique.
I'll ask questions.
I think we already talked about this slide a little bit, but could you go back to your simulated pulsar catalogs?
The catalog or the galactic or the total galactic?
It was like the simulated one before this.
This one?
Yeah, this one. I'm curious about the different shapes of the individual pulsar spectra. Is that also related to the age of the pulsar? Or?
That's a great question. It's a combination of the spectral index of the injection spectrum, let's assume, and on the age as well. So here, what was happening is basically that the pulsar has a very hard spectrum, but it encounters basically the maximum energy that you can have due to its age. So it's a combination of those parameters, and in this case you can get a very spiky one, but otherwise, but yeah, long story short, is an injection spectrum combined with their age and so cooling time of your particles.
So I guess in your data, I guess it's a little higher energy, but
Yes.
is the interpretation that we like that is part of why you have such middle-aged pulsars?
Yes, yes,
That's spikiness, or-
Yeah, sort of, yes. I mean, not necessarily the spiky thing. I mean, if you have a spike, you clearly don't have a spike in our data. So if you have, like in this specific simulation, only the spikes that we have are only at energies that are higher than TV, we don't have any data, so we don't care about. But yeah, like the argument that we need to explain this region between 100 GeV and 1 TeV, that is the energetic that tells you why we need middle-aged sources.
Thanks.
Can I ask this? I remember a few years ago, there were papers by, I think, Tim Linden and the astrologists, claiming that with Geminga and a couple of other pulsars, you could plausibly look at the gamma ray data and map that to the expected positron flux, and it matched pretty well. Yeah, what's the overlap between their work and what you guys found here?
In the works that you were mentioning, I don't think they were making an exact translation of those two. There were a few, let's say.
But they mentioned those pulsars specifically.
No. I mean, in general, they're definitely probably the most important one, but that's just a really, even just by intuition, is because of their age, distance, and power. So that's actually these three sources are the 1055 giving monogen are usually called the three musketeers because they have similar characteristics, etc. But yeah, the best way to actually, let's say, potentially constrain those signals is to combine information that you have, like your model for the positrons, and add this information about the TVL. So if you want to explain the TVL emission using the parameters that you need for that, you can directly map it into that. Definitely my group did it. I'm not sure that Tim Linden did this type of analysis. But yeah, probably Geminga with respect to a few years ago went a little bit down in the priority in explaining most of the excess, while B1055, since it's potentially very close, became a little bit went up in the ranking. But yeah, there are still some of the most important ones that we need to look at.
Just as a quick follow to Aaron's, I mean, yeah, there are a lot of groups after the 2017 results, and then in the case of the positron excess that we're pointing out, like the diffusion can't be anywhere near as low as in the rest of the galaxy. It must be in order to be creating those. You mentioned, you briefly hinted at that the path forward you think is like a very computationally expensive electrodynamic grid modeling of the region around the pulsar. Is that basically what you think the next step is to sort of push this?
Next step, in my opinion, is okay. Don't have that. Okay, the next step, in my opinion, is actually to change the computational technique. Here is full particle in such simulation, so I'm modeling both the particle of the beam and the particle of the background. I think the next step is what people have been working in the past few years, which is called MHT peak, in which basically you treat your background as a fluid, and so you don't really need to move particles, and so you save a lot, and you just need to move your cosmic rays, which are your energetic beam. So with that, I think we can actually simulate much larger domain, and not, let's say, I wouldn't say simulate the whole pulsar system or the same scales, but we can definitely start seeing if from this type of instabilities, etc., we can get some bubble-like forming or X-ray-like type of things, which is exactly what I think I will work on after this project. So people are working on that, etc. But yeah, in my opinion, we need to go up beyond the techniques currently available.
Thanks. Yeah, maybe a follow-up question to that is like where I've seen that used numerically is more looking at the cosmic ray pressure in the intercluster medium. And I'm wondering if the techniques that are being used in that regime is it scalable to this?
I think that was a hybrid thing, which is also a different technique than
Yeah.
pick. But yeah, like those are all good ways of modeling things, and like the framework is the same. So the people have been working on that for shock physics, for instability studies, etc. And then we are finding some potentially pretty interesting results. But yeah, that's the framework that I think we should push forward, considering also all the GPU work that they have just.
All right, we're over time. So let's thank our speaker again.